So I'm going to go over the related rates exercise worksheet that I gave you last week. The first couple of these, we've done similar problems before. They just give you an area formula, and they want you to relate dA dt to dr dt. So you just take the derivative of both sides. dA dt is equal to pi is a constant, so pi times, and the derivative of r squared is 2r dr dt. I think we've done that a bunch of times. So there's your relationship between dA dt and dr dt. And you can call this 2 pi r dr dt if you'd like, but you don't have to. Surface area is a very similar question. They give you the surface area formula relating ds dt to dr dt. Take the derivative of both sides, and you get ds dt is equal to 4 pi is a constant, so you keep the 4 pi, multiply by 2r dr dt. And if you'd like to clean that up a little bit, you can multiply 4 pi times 2 and get 8 pi times r dr dt is equal to ds dt. The next one has a few different situations. If r is constant, sometimes it's easier to think about r being a constant if you just give r a constant that you like for the day. Like, for example, maybe my favorite number of the day is 3. So let's let r equal 3, or any number will do. So then you'd have a volume equation to be pi times 3 squared, which is 9 pi h. And if you'd like to take the derivative of that, dv dt is equal to 9 pi dh dt. So if r is constant, you just keep r as r squared in here. Pi r squared is a constant. So you take the derivative, dv dt is equal to pi r squared being a constant, like 9 pi. So pi r squared being your constant, and then dh dt. And that's your relationship between dv dt and dh dt. Now if h is a constant, then pi r squared is your variable, so h times pi. You can rearrange this a little bit if it would make it easier for you to see this. If h is a constant, you can call this pi times h, which is your constant, times r squared. And if you want to take the derivative of that, the derivative of the left is dv dt. The derivative of, well, pi h is a constant, so you keep the pi h in there, and the derivative of r squared is 2r dr dt. So you have pi times h times 2r dr dt. And there's really nothing you can clean up about that, so that's the end of that one. Now, if neither r nor h is a constant, they're both variables, then that means you have to use a product rule here, because this is a product of r squared times h, which are both variables. So if pi stays the constant, so dv dt is equal to, you keep the pi as the constant out front, and then you do first times the derivative of the second plus second times the derivative of the first. So first times derivative of the second plus second times the derivative of the first, and the derivative of r squared is 2r dr dt. And there's really nothing here that you could simplify at all. If you wanted to bring out one of the r's, you have an r as a greatest common factor. If you wanted to bring that out, you could, but it's really not necessary. You can just leave it like that. Now the next one is a similar question. It's a physics question about power, and power is equal to the resistance R times I squared, the current. So how is dp dt related to dr and di dt? Well, here again you have a product, so you use the product rule. So you have dp dt is equal to first times the derivative of the second, which is 2i di dt, plus the second, which is I squared, times the derivative of r, which is just dr dt. And there's really nothing that you could do to simplify that. Again, if you wanted to bring an I out front as a greatest common factor, you could, but that's really not necessary. So that's dp dt relating to dr dt. and di dt. And if p is a constant, then you know the derivative of a constant is 0. So when you take the derivative of both sides, you get 0 is equal to, and then you do the product rule again, which is just what we wrote up here. So this is r times 2I di dt plus I squared times dr dt. Now, how is dr dt related to di dt? Well, you can subtract this term from both sides of the equation, and you can divide both sides by I squared because they wanted to get dr dt by itself. So it's negative, I'm going to put the 2 out in front here, so negative 2I r di dt is equal to I squared dr dt, but I'm just going to divide both sides by I squared to get dr dt by itself. And what you can do is you have an I in the numerator and the denominator, so you can cancel out this whole I and that one of those I squared, so you have negative 2r di dt divided by r is equal to dr dt. And then on the last question, 2 questions, you have diagonals of the length. You have a diagonal of a box. X, Y, and Z are the lengths and edges, so it's width, length, and height of a box. And so if you'd like to know the diagonal, and if the lengths of those sides are changing, how is the rate of change of this diagonal related to the rate of change of each one of those sides? Well, I would rewrite this as S is equal to x squared plus y squared plus z squared. It's a square root, so you raise that to the 1/2 power. And then if you wanted to take the derivative of that, how does ds dt relate to that? You take the derivative of the left, which is ds dt. And now you have a chain rule. The derivative of that right-hand side, you bring the 1/2 down front, 1/2 x squared plus y squared plus z squared. Subtract 1 from the exponent to the negative 1/2, but then you have to multiply that by the derivative of the inside. So the derivative of x squared plus y squared plus z squared is 2x dx dt plus 2y dy dt plus 2z dz dt. And that's pretty much it. The only thing that you could really do is, if you wanted to simplify this, you could move this square root down to the denominator, and you could put this as 1/2 times the square root of x squared plus y squared plus z squared, which would take care of that. And then you could multiply this by this 2x dx dt plus 2y dy dt plus 2z dz dt. And then you have a common factor of 2 in the numerator, and you have a 2 in the denominator, so you could simplify that down one more step. If you wanted to take that 2 out of the denominator, each one of those 2's is a common factor. You could factor it out, or you could just remove it from each one of those terms. So x dx dt, y dy dt, z dz dt would be up in the numerator if you wanted to make that a single fraction, but it's not necessary. Now we have the triangle. Here, this is not necessarily a right triangle. So we have a triangle called ABC, and A and B are the lengths of the 2 sides, and theta is that angle in the middle. And the area of a triangle, any triangle, is 1/2 times those 2 sides multiplied together times the sine of that angle in the middle. So if you wanted to take the derivative of this, again, I would call this A times B. So you take the derivative of the left, which is dA dt. 1/2 is a constant. Now you have first times the derivative of the second, because this is a product rule. So you have first times the derivative of sine of theta is cosine of theta, d theta dt, plus the second, which is AB. You know what, I should put a very big parentheses around that. So the second, which is sine of theta, times the derivative of AB. Well, the derivative of AB, those are variables, so you have to use the product rule again. So the derivative of AB is first times the derivative of the second, dB dt, plus second times the derivative of the first, dA dt. And that's about all we can do with this. So this is how dA dt is related to dA dt, which is here, dB dt, which is here, and d theta dt, which is here. So that would pretty much be the end of this. I can't see how this could be simplified at all. So that would be the end of that problem.